So now we get to the actual synthesis of aspirin. We're going to take the salicylic acid that we prepared in the first part and react it with acetic anhydride, essentially acetylate it, to produce our aspirin product. The net transformation going on here is taking the phenol, or the aromatic alcohol, and converting it into an ester group. Now this reaction is actually very simple. We simply take the solid salicylic acid, we add our acetic anhydride, and we also have a sodium acetate here. This is a base whose sole function is essentially just to facilitate proton transfers in the reaction mechanism. Now, the fact that we use sodium acetate is very important. And you might want to think, I won't give the secret away, but you might want to think about why we use sodium acetate specifically as the base, as opposed to something like sodium hydroxide or an amine base. Let's talk about the mechanism really quickly before we head up to lab. So essentially, what we've got here at the beginning is we've got a protonated carboxylic acid and a protonated alcohol. We need the alcohol essentially to act as the nucleophile in this case. And we have a base present. So one thing that can happen is some kind of deprotonation, but I don't want to draw direct deprotonation of the alcohol first, because the alcohol is actually the less acidic functionality here. So if I just sort of draw that base coming in here, just draw this as the negative charge and put the counter ion kind of aside for the moment. And I'm going to draw out my hydrogens. Here, this base can come and take the hydrogen off of the carboxylic acid at first, and this will essentially just get me to the deprotonated carboxylic acid. And you might wonder, well, how is that helping anything? We got a negative charge there. Well, it turns out that when these two groups are in the ortho position, that when I have the carboxylic acid deprotonated, and actually even when I don't, I can get hydrogen bonding here because of how close these two groups are. Now that hydrogen bonding, actually, essentially this proton can basically just be shared between the two oxygen atoms because they're in very close proximity. And now that I've deprotonated that oxygen, it has a lot more electron density to make a strong hydrogen bond, even close to a full bond to this hydrogen atom. And so that hydrogen atom could actually kind of jump back and forth between the two oxygen atoms here. Now, the oxygen on the carboxylic acid is not very nucleophilic in terms of kind of external reactions because it also shares resonance with the carbonyl here. But essentially, by deprotonating the carboxylic acid and kind of shifting this hydrogen to be so strongly held by that deprotonated carboxylate, I increase the nucleophilicity of the phenol right here. And so at this point, I've got my acetic anhydride, and my phenol comes and attacks the carbonyl right there, swing up to a tetrahedral intermediate. We can think about this at this point. This would create a positive charge on this oxygen, so we can simply think about these electrons from the carboxylate just taking that hydrogen and putting those electrons back onto oxygen. That will get me then to a case where I've got kind of a tetrahedral intermediate here. I've got that proton over on the carboxylic acid. I've got my alcohol here, then added to the acetic anhydride. So that's kind of a tetrahedral intermediate here that I'm drawing. This point right here. Then this tetrahedral intermediate can swing down, kick off the acetate leaving group, and this directly gets me then to my aspirin product. So a very simple reaction mechanism here, not very complicated at all. This little triangle symbol here, delta from the Greek alphabet, is indicative of heat. So we're going to put some heat into this reaction. And then we'll kind of get a crude product after we've cooled this reaction down and diluted with water. And then we'll recrystallize that product very similarly to how we recrystallize the crude salicylic acid to give us our final purified aspirin. So With all of this kind of in mind, let's head up to the lab and get this started. So here we are all set for part 2 of the aspirin synthesis. This time we actually get to make aspirin from the salicylic acid that we prepared last time. And what we'll do is we're going to take our salicylic acid, we're not going to take all of it, we're just going to take 2 grams of our isolated, nicely crystalline material, and we'll measure that out into a 50 milliliter Erlenmeyer flask. We'll add a small stir bar to that in here. And then we'll add 4.5 milliliters of acetic anhydride. To that kind of suspension, we're going to add 400 milligrams or 0.4 grams of anhydrous sodium acetate. And then we will take that sort of not soluble kind of suspended mixture over to the hot plate and we'll heat it. Now the procedure is pretty non-specific in terms of how much we need to heat it. Well, essentially what we're going to do is we're going to turn the heat on, not too vigorously, but we're going to want to heat this, fairly thoroughly until we can get all of that insoluble material to dissolve. Once all of that material dissolves, then we should be good to essentially cool the reaction and dilute it with 20 milliliters of distilled water. And then we'll sort of continue the extraction and isolation process from there. So we'll go ahead and get started and weigh out these materials. When you're going to weigh out a fairly sizable amount of mass, such as 2 grams, sometimes the filter paper or the weigh paper that's commonly used isn't really large enough to do 2 grams of material. Now in this case it might be, but a more useful apparatus or material for weighing out is actually to use a weigh boat. This way we can kind of hold kind of quite a bit of material, a little pile of material there. And so this should really help us with weighing out 2 grams without worrying about kind of overloading or spilling off the sides. So I will tare that on the balance. And then from here, I'll just weigh directly into it. It might take me a little bit with this small spatula here. So I'm actually going to pull it out off the balance, sort of weigh more rapidly, much larger amount. Put this back on the balance and see where we're at. Okay, so we're getting closer. Just going to briefly brush off a little bit that I spilled. And this seems sufficient. To add it into the small Erlenmeyer here, I can sort of bend the weigh boat along the side. Now, even that may spill a little bit, so I probably could get that in there without spilling too much, but sometimes in this case it might just be the best to just use a funnel. Next, we will weigh out the sodium acetate, and then we will take all these materials over to the hood, add the acetic anhydride, and then add the sodium acetate to that. So I brought all of the materials over into the hood. I'll now measure out the 4.5 milliliters of acetic anhydride, add that to my salicylic acid, and then add my measured out sodium acetate to that and begin to heat on the hot plate. Almost everything is dissolved at this point, but we will let the reaction heat for approximately 15 minutes to ensure full consumption of that starting material. Now that the reaction has stirred for 15 minutes, we'll take it off the plate. Let it cool briefly while we measure out 20 milliliters of distilled water. There we've got approximately 20 milliliters. We'll add this into the reaction flask. Dilute the solution. You'll notice it gets cloudy, very cloudy when we do that. It's gotten very cloudy, but no precipitate. So at this point, what we'll do is we'll take an ice bath and we'll place our material in the ice bath and hope for it to crystallize and form solid. If we do not have any solid formed in about 15 minutes, we can take a glass stir rod and really scrape the bottom of the glass. Erlenmeyer are just trying to score that surface, provide a kind of a seeding surface for crystals to grow. And so we'll let that sit for 15 minutes and see what we get. So we've left this in the ice bath for at least 15 minutes. And unfortunately, what you see is that there really isn't any crystalline material. In fact, there's kind of a liquid layer right here down along the bottom that's separate from the aqueous layer. And there's no real crystals formed or solid precipitated. And that's kind of a problem. So sometimes, I mean, the procedure didn't sort of give us the heads up that this might happen, but sometimes that's real. These type of things happen. What I'm guessing is going on here is that we've got some excess acetic anhydride that didn't react, and we probably had excess of it anyway, and so we've got some excess acetic anhydride here. And that acetic anhydride is not miscible with water, and so it's actually acting as a solvent to solubilize the desired product, which is one reason why it's not crystallizing well out of solution. I've tried scraping on this a little bit and on the glass, and we're not getting anything to precipitate or crystallize out. So what we can do is we can actually destroy that acetic anhydride simply by heating it back again on the hot plate and causing it to react with water to give you 2 equivalents of acetic acid. This should then remove this kind of immiscible layer, since acetic acid is miscible with water. And then we might have better success crystallizing the material by putting it back in the ice bath and letting and scraping the glass for a little bit. So I'll place this back on the hot plate, and I'll turn the temperature back on. And heat this for maybe about 10 to 15 minutes. So now that I've heated that for a while, I can sort of look at it, and you see that most of that oil is gone. Now there's still a little bit of oil here, but I heated it above the melting point of the product. So some of this oil may just be oil from the product. So I'll let this cool a little bit and then put it in the ice bath, and we'll see if we can get some crystals in a little bit. So now we've left the Erlenmeyer containing the product in the ice bath for quite a while now. Actually, all of the ice is melted. And what you can finally see, it took quite a while for it to precipitate out, but now you can see kind of a nice white, solid, not very crystalline, perhaps, mostly more kind of precipitate-like, but there's now material here, so we can collect this now by filtration. So we've got our crude aspirin here. I've brought along a spatula just to help scrape it out if we need to get it on the filter. We've got our filter paper and some distilled water just to rinse the crude material with on the filtrate. So I'll go ahead and turn on the water aspirator at this point. We'll grab a piece of the filter paper, put this onto the filter, and then wet that to make sure that it adheres nicely to the filter. And that should be well sealed now. And we'll take our crude aspirin here, sort of scrape it up a little bit with the glass stir rod, get everything kind of suspended in solution. I'm not going to worry too much about dumping the stir bar onto the filter paper. We can always pull it off after we do. So we'll kind of go ahead and just dump this material on. Saw the stir bar go forward. It's kind of a clumpy material. You might even notice where it looks like we're getting a very, very small amount of stuff going through the filter there. That's all right, but it is a source of mass loss. We've got some stuff still on here, so we'll rinse that forward with some distilled water. Maybe we'll rinse one more time. We don't want to rinse too much with excess water, because aspirin is somewhat water soluble, which we're grateful for, because otherwise it wouldn't work very well in the body. So we don't want to lose too much in the process. But there we go. We'll sort of pull air through the system now. As you can see, the solid filtered material. Kind of a powdery white solid. not unlike the powdery salicylic acid before recrystallization. We'll pull air through this for a while, collect it, put it in the oven to dry, and then get a crude mass and a melting point and NMR sample prepared for the crude material. We'll then recrystallize the crude material very similarly to how we recrystallize the crude salicylic acid, and then get melting point, NMR, and final mass data for the recrystallized aspirin. We will now prep a melting point sample and a crude NMR sample for our crude aspirin product. Now at this point, even though we only used a very small amount here for the melting point sample and for the NMR, we have kind of a smaller amount of product than we did in the previous reaction, and so the amount that we took out may not be negligible. So I'll actually take this back to the balance and weigh it again so that I know exactly how much I have before doing the recrystallization so that I can accurately calculate a percent recovery. So now I'll go ahead and recrystallize the crude material very similarly to how I recrystallized the crude salicylic acid. I've got some hot water already boiling on the plate here. We'll add some of that hot water into my solid crude aspirin here to enough to cover the bottom, and then we'll put this on the plate, add some more of that hot water, and then probably place the watch glass on top just to prevent any vapors from kind of escaping from losing volume. And then we'll boil that solution to really try to get everything dissolved. And once everything's dissolved, we can then take it off the plate and let it cool.
So it appears that essentially everything is dissolved. Be a little bit of material here. It's a little hard to see, but we'll go ahead and remove this and let it cool now to recrystallize. Unfortunately, rather than getting a good recrystallization, what we have instead is a case where we got the product to oil out. So here you see it's cloudy, not really much in the way of solid material, and it may be kind of difficult to see, but there's some really kind of oily material around and along the bottom of the flask. This is probably due to having the hot plate pretty high, and actually some of that material melted. It got above its melting point. Aspirin melts at a lower temperature than the salicylic acid. So melted and then has formed kind of an insoluble layer or kind of bubbles within the aqueous layer. So we're going to have to try to solve this. For right now, let's just try a quick simple fix. Take this back to the hot plate, see if we can just heat the solution back up, get this material maybe to go into the solution, and then perhaps it will crystallize upon cooling. We've put this back on the hot plate and let it warm up quite a bit. The solution's re-clarified, as you can see. Unfortunately, we haven't managed to get rid of all of the oily material. There's still an oil droplet there in the middle that you can kind of see. However, we seem to have gotten the material much more soluble, and we may just have to attempt the recrystallization still with a little bit of this oily material here. So a bit of a challenge here. We've sort of done the best that we can. We'll sort of stir this up again just a little bit. Break that material up a little bit. And now we'll go ahead and take this off and let it cool. So although this isn't the prettiest and possibly most successful recrystallization ever, we did actually get solid material to come back out of solution here. It may not be perfectly white in all places, but we'll go ahead and filter and collect this, and then we'll get our final kind of NMR and mass and melting point and just see what the results are. Rinse one more time. And then we'll let that dry for a little while before we scrape it into a tared beaker, put it in the oven to dry for a while, and then get a final mass, melting point, and NMR characterization.
you.